Okay, so, right, sorry. So let me start fresh here. Arc length refers to the length of a graph, and it's easy to find if your graph is a straight line. How do you find the distance of a straight line? The distance between 2 points. Using the distance formula. So the standard notation for distance is s, lowercase s. So that's what I'm going to use. So the length is s, which is just the square root of x2 minus x1 squared plus y2 minus y1 squared. Now we're going to use our nice notation, which is related to calculus, as you've seen before. We're going to call this delta x squared plus delta y squared. Okay. So, what if it's not straight? Approximate. So recall, in the same way that we approximated area with rectangles, how are we going to approximate length? Using straight lines. So the easy case, you've got a straight line, you just have delta x and delta y. The hard case is when the graph is curvy. So how are we going to get to a solution for the hard case? We start by approximating the graph with straight line segments. Okay. So here's the key question. What is the length in the approximation? How are we going to figure out the length when we break it up into a bunch of line segments? Add them up? Yeah, exactly. So it looks something like, so how do we find the length of each little line segment? Distance between 2 points. We're going to use distance formula on each segment, and we're going to add them up. Looks like this.
Are we supposed to have two different steps here? One for the x and one for the y?
So this is, it's implied. So for our purposes, we know what we're going to want to do. We're going to want to make it so that all the delta x's are the same size. And then delta y is whatever delta y is for that delta x. So really, so delta x is constant, but delta y is changing, and we sort of understand that just because we do it. This is the way that we do it all the time. Does that make sense? I think that makes sense because we've done that. We've done this before. Okay. So it looks like this. So now we're going to do, again, the same technique that we always do. We're going to just rewrite this in summation notation. So it just looks like this. And again, this isn't precise summation notation. This is sort of just casual summation notation. So here's the problem. This doesn't look exactly like what we normally want. We normally have summation of something delta x, and then we just turn it into integral of something dx, and we know we're good. But we don't quite have that here. We've got a sigma in front, but we don't have a delta x at the end. So what can we do? Well, what we do is an algebra trick. Now, before I show you this, let me just say that algebra, boo hiss, and all that. However, I'm going to show you this and then explain how what I'm showing you is related to higher math. So the derivation I'm about to do, you don't need to necessarily memorize the derivation for this class, but having seen this will help you in future calculus classes.
Is this the multiply by everything to cancel out stuff trick again?
Sort of. So let's take a look. Okay. So I'm going to do this very bizarre trick. I'm going to multiply by the square root of delta x squared divided by the square root of delta x squared. Now, obviously, I can do that, but the question is, why would I do that? Well, why I would do that is what you're about to see. So the top part of the fraction obviously just simplifies delta x. The bottom part is where it gets clever. I'm going to move that under the other radical for the purpose of combining them. One square root divided by another square root, you can just combine it. So now I've got a fraction inside the square root. I can break up that fraction. And now something lovely happens. And now we can pass to delta x becoming dx. And what happens to this entire expression? What does it become? The integral of what? The square root of what? I'm asking.
1 plus delta y dx squared.
1 plus, wouldn't that be slope squared?
Yeah. If delta x passes to dx, what happens to delta y?
Also is. No, I don't know.
It would be all like if it's a
If delta x passes to dx, then what happens to delta y? It becomes dy.
And that's just the derivative.
And what is dy over dx? It's the derivative. So this is the one time in the entire semester where it's helpful to actually know what we talked about regarding differentials before. So remember the definition of a differential, and I'm just going to say this really briefly, then we'll pass by. So we defined what dx is, and we defined it separately. We said it's delta x, it's the limit of delta x as delta x goes to 0. And remember, we take delta x going to 0 in order to turn the approximation into something exact. Okay, well, what happens to delta y? dy is the limit of delta y as delta x goes to 0. And that was the definition of how we define these differentials. So this is something that I actually mentioned in passing before. This is I'm almost positive last time we're going to see that. Okay.
If you look for delta y, like how does the meaning of the equation?
So let me just mention that. Oops. Okay. So first of all, let me say this. Sometimes we write this whole square root dx thing as ds. I'm not going to go into an explanation of why that is. It's notation that'll come in handy later. So we could think of s equals the integral of ds. Okay. In higher math, sometimes we write this. Not going to go into that as well. I just want to mention it because you might see it later in a future class. Now, to answer your question, we introduced delta x in the algebra trick. We could also have introduced delta y. And if we did that, then what would happen?
We'll be integrating across delta x.
Yeah. That would mean that y was the variable, and then we'd be taking the integral of the square root of dx dy squared plus 1 dy. So we'd be doing the exact same thing, but with y as the variable. So we could do this, for example, if x was a function of y. So does that answer your question?
Like,
Sort of?
there's no difference between the meaning of them. Like the meaning of the is what I don't. difference is very.
Oh, we're going to do better than that. Let's do some examples. So here we've got a function y equals x minus 1 to the 3 halves. X goes from 1 to 9. So what is the length of that graph? So what do we do?
Take the derivative of this.
Okay. So I want to say S equals the integral of what?
1 plus plus or minus.
Oh, right. The formula. Here we go.
Square root.
Okay. So the square root of 1 plus,
The derivative of y.
yeah. So I guess the formal notation is dy dx. What's a nice shorter notation for that?
Y prime.
Y prime. Squared dx. And what's missing?
From 1 till 9.
From 1 to 9. Okay. So now we should continue to go ahead and do it. So the integral from 1 to 9. So what is y prime? So actually, let's do that on the side. Y prime equals what?
X minus 1.
So 3 halves x minus 1
1 over 2
to the 1 half. Right.
times.
And you do chain rule, but the derivative of the inside is 1, so it's no problem. Okay? So, square root of, so now we actually, let's just do this on the side. What is y prime squared? Yeah. Actually,
9 over
yeah, actually, no, I'm not going to do it on the side. I'm just going to stick it in there. Okay. So 1 plus 3 halves x minus 1 to the 1 half squared dx. Okay? So when you square it, what do you get? You get 9 fourths,
and that's x minus
just
1.
x minus 1 dx. Okay. So now what do we do? Well, I think we should actually simplify and distribute in there and see if we have something nice or what's going on. So this is 1 plus 9 fourths x minus 9 fourths all square root. Okay. So this is 9 fourths x minus 5 over 4 square root of that. Okay. Now how can we do this integral?
Turn it into u.
Yeah, we've done this kind of integral before. We have to do a u-sub. We have to do a substitution. So what is the u going to be? It's going to be that inside business, 9 fourths x minus 5 fourths. So du equals 9 fourths dx. Now all we want to replace is dx, so we know that 4 ninths du equals dx. Okay. So now we've got the integral of the square root of u du with a 4 ninths, and I'm just going to put the 4 ninths in front. Now how do we do the integral of the square root of u? Yeah, that's really just u to the 1 half. So the integral of that is u to the 3/2 and then times 2/3. Okay. So this is 8/27 u to the 3/2, but u was 9/4 x minus 5/4.
To the 3/2.
No. I'm sorry, yeah, u to the 3/2, right. U to the 3/2. And what still needs to be done?
From 1 till 9.
From 1 to 9, the boundaries, don't forget that. Okay. Oh, okay. That's going to be a little messy, but that's all right. So at 9, you get 81/4 minus 5/4 to 3/2 minus... Okay. And then you can just do arithmetic. I don't think this simplifies nicely. Okay, so once again, the easy part, well, actually I won't say that. I'll say there's the setup, which is actually pretty easy in these problems because it's just a formula. But there's going to be lots of little manipulations that you have to do the problem. Okay. So about the next one. Actually, first I should say, any questions on the first one that we just did? Okay. Next. So find the length of the graph. Y equals 1/3 x cubed plus 1/4x, where x goes from 1 to 2. All right. So the length is s, and what is it?
From 1 till 2, integration from 1 till 2. Square root of +1 of 1 plus.
Dx. Okay. So what is y prime?
X to the x squared
plus 1/4.
X squared plus, that's, okay, if it's not clear, that's 1/4x, not 1/4 x. So it's 1/4x. So how do we take the derivative of that?
Rewrite it.
Yeah. So this is, so let me actually fix that. Okay. So what's the derivative of that? Yeah.
Negative x to the negative 2.
Right. So what you actually have is 1/4 x to the -1. So what's the derivative of that?
Negative x to the negative 2.
Right. Negative x to the -2, and then with the 1/4 still in front. Okay. All right. Now. I think that's supposed to. Okay. To continue. All right. So let's do this work. I want to do this work on the side because it's about to get messy. So what happens when you square this? So we need y prime, and we need to square it. This is x squared minus 1/4 x to the negative 2 squared. So what is that?
X to the 4 minus 1 to the 16.
Well, yeah. So the easiest way to do this is to remember that a plus b squared, or in this case a minus b squared, I guess, is a squared minus 2ab plus b squared. So I'm going to use that mental shortcut to write down what this is when you square it. Now, if you don't know that shortcut, you should just FOIL it. Okay. But I'm going to use that algebra shortcut. So you get minus 2 times x squared times the second one, which is 1/4 x to the negative 2, so 2ab, and then plus the last one squared. So what's the last one squared? It's going to be 1/16 x to the negative 4. Okay. Now, let's simplify this. This is x to the 4th. This last thing is still 1/16 x to the negative 4. What happens to that term in the middle? Yeah, you add the exponents. What happens? You get x to the 0. What's x to the 0? It's just 1. So this is just minus, 2/4. So just minus a half. Now, I did all that work on the side because I would have found it really irritating to have to write over the entire integral for every step that I did this. So I just wanted to do it on the side because I thought it'd be neater. Okay. So now that I know what y prime squared is, okay. One plus this thing, x to the 4th minus a half plus 1/16 x to the negative 4 dx. Okay, so now what? So we got to integrate this thing. So, well, what's the first thing to do? The first thing is we can do a little simplification in there. So what happens when you simplify? Get x to the 4th plus 1/2 plus 1/16 x to the negative 4 dx. Now, what do we do with that? Well, what to do with that is actually suggested by where this term came from. So the step before, where did all this mess come from? X to the 4th minus half plus 1/16 x to the 4th. Where did that come from? It came from, well, not just the derivative, but it came from squaring the derivative. So we saw that when you square it, you get x to the 4th minus a half plus 1/16 x to the 4th. Okay. But now we've got x to the 4th plus a half plus 1/16 x to the negative 4th. Now, if we're clever in our algebra, we're going to realize that this is also something squared. Because this thing came from having a squared minus 2ab plus b squared.
Oh, so that's
So what do we have now?
x squared plus.
Now we've got x squared plus 2ab plus b squared. So that's what squared? That's just a plus b squared. So before we had a minus b squared, and now we've got a plus b squared. And this is helpful because we're going to take the square root of that. So this is just x squared plus 1/4 x negative 2 squared. Wasn't that lucky? Okay. So now we can do the easy simplification. This is just x squared plus a quarter x to the negative 2 dx. And now we finally have an integral that's easy to do. X cubed over 3 plus, it's going to be negative x to the negative 1 from 1 to 2. So plug in 2, you get 2 cubed over 3 minus 1 quarter. 2 to the negative 1 is just 1 over 2 minus 1 cubed over 3 minus 1 quarter. Well, 1 to the negative 1 is just 1 over 1. Not very interesting. So you get 8/3 minus an eighth, and then minus 1/3 plus 1 quarter if you distribute the negative. We got to work that all out. So let's see. So this is all over 24. It's going to be 64 minus 3 minus 8 plus 6. So that gives you, let's see, 59 over 24. Just want to give it to me as a decimal, that's fine too. Plug it in, use a calculator. Okay. So, notice that the first problem and the second problem started the same, but solving them took two very, very different paths. So it's a question of what trick are you going to need to use in order to actually do the integral. And honestly, these are the two main tricks for doing integrals when you're doing arc length problems. So, now both of the, well, the first one is a trick that we've seen before. We talked about this. When you have when you're trying to integrate a radical with a linear expression of x in there, you should do a u sub. That's a trick that we've seen before. But the second one, this is something we haven't seen in a while. So technically what we're doing in this problem, in the third and fourth step, technically we're completing the square. Not completing the square, we're actually finding what is being squared. But here's the trick for arc length problems, and trust me, the problem will always work out nicely. What'll always happen is you'll see your negative half plus 1 flips it to a positive half. So that's going to be the clue as to what it was that you should have that's squared, which is, in other words, just the thing that you had, very similar to the thing that you had before. Only now it's going to be plus instead of minus. So arc length problems are very hard. It's very hard for an instructor to make up a problem that works out nicely, and this is one of the few ways to do it. So this is pretty much the trick that you're going to see. Is it a trick? Yeah, it's a trick, but there's only one. Okay. All right. The main thing, and what I think is most important, is this idea. Set up but do not solve given a particular function. Because this says, do you actually understand the idea of what is arc length without having to worry about all the algebraic tricks to actually solve the thing. So how do we do this? You tell me. Sorry?
Find the derivative first.
Okay, so we know we're going to need the derivative.
Right? Which is
Yeah,
product
and we're going to have to find the derivative using the product rule. Which is what?
E to the x times 1 plus x
Right. So there's y prime.
and a square expression.
Right, and we're going to need to square it. So not going to worry about actually writing out what it is squared. So what is the arc length? Okay, and what is that? Integral of square root of 1 plus